My name is Samantha Kukulek. I am attending Unity College with a major in environmental studies, and this is my statistics final. I am focusing on the Redwood Forest in California. Specifically, I am focusing on the Redwood Forest and sudden oak death. Sudden oak death directly in relation to the tin oak trees and the redwoods and the lack of regeneration gives the tree a mortality rate of 63%. Looking at the redwood forest through an aerial view rather than the traditional linear view, the canopy coverage seen is able to give a stronger view of where the sudden oak death has spread since the pathogen was found in 1997 to present day. My research question states, has the pathogen sudden oak death been the cause of the inability for tin oak trees to regenerate, leaving holes in place of their stumps and a height increase to other redwood trees? My data collection and source. I focused on the connectivity part. In the study of the importance of connectivity in the spatial pattern of sudden oak death, various techniques were used that I had found during my studies. These included an statistical regression, least cost path analysis, and model selection. Connectivity can best be described as a state of being connected or connective, and in environmental science, connectivity can be used finding the importance of various techniques and patterns. The hypothesis determined that the connectivity, when added to the environmental conditions, creates a stronger look at spatial distribution of sudden oak death. In this, the connectivity can be best and most apparent when measured using biological metrics that show the spread of the pathogen in relation to the effects of landscape structure. Overall, this hypothesis hopes to prove the importance of environmental variables and connectivity are equal. Along with my hypothesis, I am including my null and alternative. The null hypothesis states, there is no statistical significant relationship between the outbreak of the pathogen sudden oak death and the increase of the mortality rate and inability to regenerate in tin oak trees in the redwood forest. If a tree catches this pathogen, it has no difference or issue in the reability to grow new roots where this tree had fallen. My alternative hypothesis states that since the outbreak in 1997 of sudden oak death, the mortality rate and inability to regenerate of the tin oak trees in the redwood forest has increased. If a tree catches this pathogen, there is a significant difference in the regrowth of roots where the past tree had fallen and affects the reability to grow new roots. My statistic and process used. My best found sample size for this research study is the number of trees affected by the pathogen sudden oak death and how it affects the canopy coverage directly. As for statistical techniques, I have found that a histogram is best used to show my research and data. A time plot is also reliable if the amount of trees that have died and not regenerated from 2008 to present day can be determined. Further research that I found were on rain traps as well as the overall survival of spores. By introducing the concept of looking overhead at the forest rather than the trees we see, I chose to research canopy coverage in the redwoods from the time the disease was found to present day. While doing this, I found that vector imaging has not been increased very much to present day. I have found one image and graph that helps show and predict the potential distribution of sudden oak death in California. And by using this vector imaging method to deal with presence-only data in ecological analysis over a range of scales. As shown in this image, you can see that the spread on the left side, the red, is the pathogen. As it spreads up, the amount of trees is lacking. You can see this from the very tip of California to the end. Another graph that I found that I will be including is rain traps data. In this, you can see that the height of it is the spores per liter of rainwater for storms occurring. Of the 6 distant traps placed under the forest canopy 5 meters away from the infected oak trees, 2 were positive for sudden oak death during the sampling period. Viable spores of sudden oak death were shown to be carried in rainwater, soil, leader, and stream water. The presence of diseased oaks at all elevations on hillsides and the above-ground nature of the disease suggest wind-blown rain or rain splash as a common mechanism for movement of spores. My last graph is the survival of spores data. Both types of spores were killed by the drying process at 30% room temperature in the dry filter treatment. You can see this in the top 2 graphs. The thick-walled resting spores survive better than the zoospores in both the water and moist treatments. The zoospore survival averaged less than 20% at the end of the 30-day period, while the other survival at 30 days in water and on moist filters still averaged 75% and 41% of starting values. This is shown at the two bottom graphs. My data interpreted. The data discovered and interpreted is very certain and fully reliable. It pertains directly to the research question while answering both hypothesis questions, ultimately discovering that the alternative hypothesis was proven correct. This was proven correct because of the direct link of the pathogen's sudden oak death to the regrowth of redwood forest to oak trees, resulting in the 63% mortality rate. In conclusion, the alternative hypothesis has been proven correct. Since the outbreak in 1997 of sudden oak death, the mortality rate and inability to regenerate of the oak trees in the redwood forest has increased. If a tree catches this pathogen, there is a significant difference in the regrowth of roots where the past tree had fallen and affects the reability to grow new roots. For my future research, I hope to focus over the next few months and years. I would imagine that the growth of vector imaging would result in a stronger study and create a way to research the canopy loss of the forest due to the pathogen's sudden oak death. My canopy coverage analysis can be proven in this image shown on the left. The dead trees are mixed with the living redwood trees, and this shows how far the pathogen has spread. My reflection and also future research. The overall expected outcome of my research study was to find the mortality rate of oak trees in the redwood forest due to sudden oak death. I found that over my study over the course, I was able to identify this a little more than I started with and gained a lot of information on the pathogen itself. I experienced no change in my expected outcome. However, I did find myself struggling to find studies to back up existing beliefs. I'm not sure if I would have changed anything about my study, including my data collection, assumptions and limitations, research, and literature review. One thing I may have changed and went in more depth of research into would have been my interpretation and analysis. I believe with more detail, I may have had a much easier time finding detailed studies for my interpretation and analysis. I find that further research may include the additional look at vector imaging. While researching this topic, I found that many of the studies use vector imaging to overlook the canopy coverage in the redwood forest, but the majority of the images were not valid and had just recently become applicable for studies to use. Over the next few months and years, I would imagine that the growth of vector imaging would result in stronger studies and create a way to research the canopy loss of the forest due to the pathogen's sudden oak death. Finally, my research and reference page. I take no credit for any information that was in quotes, and I take no credit for any images. And that is the final of my statistical study on redwood forest and sudden oak death. Thank you.